In this video, we're going to look at limits. We're going to evaluate limits using limit laws, and the limits that we'll be taking will be limits of rational functions where the numerator and denominator are both polynomials. For our first example, we're going to look at the limit as x approaches -1 of x squared minus 1 over x plus 1. If our function is continuous, so here we have a rational function which can be discontinuous, but if it's continuous, all I need to do then is put the value of -1 in for x. But if we try that, we see that the denominator becomes -1 plus 1, which is 0. Okay, so it's not continuous. However, the numerator is -1 squared minus 1, which is also 0. So we call this what's known as a 0 over 0 indeterminate form. We don't know whether or not the limit exists. That's why it's indeterminate. So we're going to use a special theorem in order to evaluate these. Here's our result that we're going to use. Suppose we have two functions, f and g, and they're equal to each other, except perhaps when x is equal to a. So f and g are always equal to each other, except when x equals a maybe. If this is the case, then the limit as x approaches a of f of x and the limit as x approaches a of g of x will be equal to each other. And the reason for that is because limits ask us what's happening with the function when we are close to but not equal to a. So we say we're not going to require that they be equal at x equals a. So what's happening to f when x is close to but not equal to a? What happens to g when x is close to but not equal to a? Well, because the two functions are equal when when x is not equal to a, this limit result is true. So what we'll do is we'll take our rational expression and we'll factor it if we can. The numerator factors as x plus 1 times x minus 1. Now, when we have these rational functions, if the numerator and denominator both approach 0, you should have a common factor between them. Okay? And that common factor will be the factor that's equal to 0 when x is equal to our particular value. So when x is equal to -1, x plus 1 is 0, and so is x plus 1 up here. So these two will reduce, and we'll just be left with the limit as x approaches -1 of x minus 1. Well, now this is a continuous function. Okay, it's linear, and since it's linear, we can use direct substitution. Because it's continuous, I can just substitute -1 in for x. That's where that -1 comes from. And so we have -1 minus 1, which is -2. For our next limit, we have something a little bit more complex. 2 quadratics as a fraction. All right, so I'm going to do the same thing. I'm going to see what happens if I substitute 5 in the denominator. Well, I'd have 5 squared minus 7 times 5. Now let's just stop for a moment. 5 squared is 25. That's minus 35, so I'm at -10. And when I add 10, I get 0. Aww. Okay, well, let's look at the numerator. The numerator, we're going to get 5 squared, 25 again, plus 6 times 5, which is 30. So 25 plus 30 is 55, but then we subtract 55. We get a 0 over 0 indeterminate form again. So there may be some hope that these two will factor. Well, they'll factor and reduce if we're really lucky. Now, as I mentioned before, as x approaches 5, we want each of these factors to be 0. Okay, so what I should know is that a factor of x minus 5 should exist for each of my polynomials, which makes it really easy when it comes time to try to factor it. So let's see. X times something should give me x squared. Well, that would have to be x. X times 5, -5 that is, times something should give me -55. Oh, well, that would be positive 11. Right? Because -5 times positive 11 will give me -55. That's how it should factor. Now I can check the outer and inner terms. The outer product would be 11x. The inner product would be -5 times x, which would be minus 5x, which is precisely the 6x that we have up here. Let's try the same thing down in the denominator. X times something should give us x squared. Well, x times what? X would give me x squared. I want to multiply -5 by something to get positive 10. -5 times -2 would give me positive 10. And if I do all my work like I'm supposed to, the outer terms would be x times -2, which would be -2x. The inner terms would be negative 5 times x, so minus 5x. Again, that's exactly what we got in the middle there. And that's exactly how it will factor. Once we have that, now we can reduce. Those two factors will go away. And this reduces to limit as x approaches 5 of x plus 11 over x minus 2. So now I try direct substitution again. That is, I use the continuity of my function. Well, when x is equal to 5, we're going to have 5 minus 2 in the denominator. That's 3. 3 is not 0, so our function here, x plus 11 over x minus 2, is continuous at x equals 5, and so all we have to do is plug 5 in. So we have 5 plus 11, so x is 5, 5 plus 11, x minus 2, 5 minus 2. That would be what, 16, and that's our limit. In our final example, we're going to do something slightly different. Okay, we want to know what happens as h approaches 0 of 8 plus h quantity squared minus 64 over h. Once again, I should probably go ahead and say, well, what happens if I let h be 0? Well, it's quite obvious the denominator is going to be 0 there, isn't it? Because we just have h equals 0. The numerator, on the other hand, is 8 plus 0 quantity squared minus 64. Well, 8 squared is 64. 64 minus 64 is 0. So we, again, have a 0 over 0 indeterminate form. Well, this time, yeah, we factored in the other two. We actually could factor, and if you want to, try it on your own. But what I'm going to do instead is, because I have this square here, it's really begging to be expanded. Okay, so 8 plus h quantity squared means I'm going to take 8 plus h times 8 plus h. Okay, and so if we expand that, we'd have the first would give us 64, outer would give us 8h, inner would give us another 8h, so for a total of 16h, and then the last would give us h squared. So let's just expand out. 64 plus 16h plus h squared minus 64. Okay. If things work out well, this will reduce. And notice the 64 minus 64 is 0. And here we have a common factor of h in the numerator. So let's factor that out. All right, so we were left with 16h plus h squared. We factored out an h. The h's will reduce. Okay, and when they reduce, we'll be left with 16 plus h. Now this is not even a rational function. Since it's not a rational function, it's now a polynomial. We can directly substitute the h equals 0 in, and we end up with 16 plus 0, which is 16.